So what I will do today is to give you a flavor of the kind of things which we do in the computational sciences group. And in my group, in the computational sciences group, it's a very interdisciplinary team. In a group of 10, to give an example, 4 of them are computer scientists. There is a computational biologist like me. There is a physicist, two statisticians, and a molecular biologist. So only 10% of the people are from technically biology background. NIH, which is funding most of the research in US, the director of NIH has identified that to solve the problems in biology and medicine, we need to bring in people with quantitative skills, mainly mathematicians, statisticians, and physicists. And there is specific funding for people from engineering to come into biology. So, what I would, if I will consider this successful, if any one of the students will take up a graduate level course in computational biology, or at least do a project, finally a project in this field. And it's not very hard to get into this field. And there are a lot of opportunities to do higher studies in this area. So, I have never done studied biology after my 10th standard way back. So I'm going to give you a very, very brief understanding of idea about molecular biology. Without that, I cannot put the rest of the talk in context. My background in biology is all self-taught, so I have a sort of abstract level knowledge of how things work at the biology system. So I'll try to do that. Then I'll try to tell how we measure things within biological systems. And without measuring things, you can't compute with the data. And you can, how do we make some inferences and models from these data sets? So that's what. And mainly the data sets which are generated in molecular biology is huge. And it's a big data problem. That is where people from computing or engineering background comes into this. So that's where we have opportunities. So then I will try to give some examples of some projects which we do, where we try to make sense of or make some inference about how to treat a cancer patients or whom to treat aggressively and things like that. Now, so how do we understand the biological system like human body? From the organismal level, it's a very complicated system, but you can take things apart. For example, here, is there a pointer here? Yeah. Alright, so the next level is to have organ system level. For example, you have the urinary tract system, where you have the kidneys, uterus, bladder, and urethra. And a tissue system is composed of specific tissues, for example, the bladder. And within the bladder, you can have several kinds of cell types. And each of these tissues is composed of multiple cell types. And each cell is composed of several molecules. And of course, then, even if you go further down, you have atoms and electrons and quarks and stuff like that. But for a biologist, the most fundamental thing is the cell, because the cell is the smallest independently functioning unit of the body. So that is where most of the biologists try to understand organisms or even tissue systems by studying how a cell works. A human body has something like 500 cell types. You have skin cells, or you can have pancreatic islets. There are 400 to 500 cell types, depending on whom you ask. And when I say cell type, every cell type has a very different set of expression profile, meaning the molecules that are present in the cells are different based on the cell types. And that composition is controlled by a very specific program called gene expression regulation. And a healthy human being will have all of these transcriptional profiles very well controlled. And if any disease can be thought of as a misregulation of the transcriptional program. That's how I kind of think about a biological system. Now, this is again a cartoon representation of how a cell works. In a eukaryote, like a human, you have a cell membrane. Inside there is a nucleus. Within the nucleus, there is chromosomes, which has genetic material. I hope everyone knows some basic understanding of how these things. Nowadays, everyone studies some level of molecular biology, I believe. And each chromosome can be thought of as a linear stretch of alphabets comprising of 4 letters, A, T, G, and C. And that letters encodes the information about a gene, which then transfers into a protein and things like that. If you study molecular biology, you'd be amazed to find the similarity of a working of a transcriptional program and an abstract Turing machine. Computer science students here will know about abstract Turing machines, and the cellular working transcriptional program is not too different from that. So, like I said, DNA is the static genetic material which get translated into RNA and transcribed into RNA and translated into protein, which will define the characteristics of the cell type. Now, if you cells divide, when we grow, cells divide, and in that process, the chromosome, the genetic component material has to be copied, like a program, you copy a file. And that process is very well regulated, but it still can have some mistakes. And that can give you some diseases, like, for example, cancer. And that's why if you smoke, you have a much higher chance of getting lung cancer, because that nicotine is a mutagenic agent. So the copying process may not be that perfect. So, how do we study how a cell works? So this is what I was saying. You have the DNA, it gets translated into pre-mRNA. There is some process called splicing. There are a lot of details into this. A typical molecular biologist will take 6 years to study this process, and I gave you that summarized in 5 minutes. But to understand the computational aspects, that's enough, I believe. So, the traits of a cell, and of course from the cell to a tissue and tissue organ system, is basically determined by protein and the metabolites. For example, there is an organ called pancreas. Pancreas has islet cells. They have a cell type called beta cells which create insulin. If you think about it, when you eat anything, you have glucose in your blood. And there are cell types which sense the amount of glucose in your blood and then generate the amount of insulin necessary for that to process that glucose. If that process is misregulated, then you get what is called diabetes. So that's what I was telling you. This regulatory process is like a control system, very, very well regulated. Of course, it is not engineered. It is evolved. Natural selection has given us the ability to do that very well regulated system. And for example, if you want to understand what happens in diabetes, you have to understand what are the transcriptional profile in the pancreatic and islet cells of a normal individual and the diabetic individual. You can compare what happens and things like that. That is a very reductionistic approach to understanding, but it has taken us way forward and at least we have made some progress into how we treat a particular disease. So I'm going to use some terminologies downstream, so I'm going to define that. The set of all mRNAs. mRNAs are the molecules that get transferred from the DNA. DNA is static. In your body, there are trillions of cells. The DNA content is exactly the same, but you have different cell types, which means that you have different proteins. How does that happen? Because there is a regulatory process which is happening in different cell types. The holy grail of in molecular biology is to understand how that transcriptional process happens. And one way to understand that is to measure things. For example, you can measure pancreatic islets from deceased individual, meaning people who have type 2 diabetes, and who doesn't have that, and see what happens, what is the difference between this, and how can we mitigate the differences of things like that. Now, the complication is that the mRNA component of a cell is determined by several things, like the genetic alterations. Like I said, the DNA can be mutated when it gets copied. The chromatin structure. What I mean by that is the DNA is, there are 3 billion nucleotides in a human cell, and that is packed into a very small area. And the 3D structure of the chromatin is also cell type driven. These are all things which we are realizing now. We don't have a complete understanding of this, but we know for sure that the chromatin structure changes the transcriptional profile. The microenvironment, for example, the transcriptional profile of a cell is dependent on what other cell types are surrounding it. And the proteins, there's a self-regulatory, there are feedback processes, negative and positive feedback processes, like any control system. Obviously, that is not designed unless you are a believer in creations, but most scientists believe that it is natural selections that engineer these mechanisms in a cell. So, right now what happens is that we have technology to measure the transcriptional profile of a cell. It's expensive and it creates a lot of data. For example, you can take a cell from a body and measure how many molecules of a particular gene is there, and a genome one. Like I said before, the holy grail of molecular biology right now is to understand all cell types. Like I said before, there are approximately 400 to 500 cell types, but most people believe that there are new novel cell types present in human bodies we don't know, and a lot of experiments are done to identify all cell types. And then the most important thing is that we want to know how these genes are regulated. Because, to give you an example, a lot of these diseases can be thought of as disruption of this regulatory process. Alright, that's all the biology I'm going to talk. Now I'm going to talk about, with that as a background, I'm going to talk about some cancer biology. There's a typo there, sorry about that. And then I will try to tell you how machine learning is helping to solve some problems in biology. What is cancer? Cancer, by definition, is uncontrolled growth of cells that can form into a lump. You can have a tumor of the breast or lung, and not all tumors are cancers. If the tumor attains the property to metastasis, then it's actually called a cancer. Cancers are tumors that can travel. The malignant tumor is another name for cancer. And pathologists can identify, when you do a biopsy, the pathologist can look at it and say whether it is a malignant tumor or a benign tumor. So, how does a normal cell become cancer? In a normal cell, for example, your skin cell has the capacity to regenerate. If you have a wound, it will make new cells and then it will stop after the wound is healed. So there is a regulation, there is a control program which tells that there is enough cells to close it, no need. But if that regulatory process is not working properly, then it will keep dividing. That is cancer by definition. And that happens. Right now, we know how that happens. There are certain genes in the cell called oncogenes, and if there is mutations in the oncogenes or tumor suppressor genes, oncogenes are like accelerators and tumor suppressors are like brakes, and these two are working in perfect control for a normal cell, but loss of any of those due to some mutations can give you cancer. And if you take a human being over the age of 40, for example, there will be cancer cells, but not everybody will get cancer, because if your immune system is working, immune system will recognize it as something pathogenic and control it. So, a cancer to manifest as a disease, it has to develop the ability to evade the immune system. There are so many characteristics for a normal cell to become cancer. And it becomes very, very complicated because it's a very nonlinear system. Like I said, the transcriptional program is regulated by proteins within the cell. And that's a very nonlinear system. There are some proteins, it is very slight increase in that protein can generate transcriptional changes in a whole lot of genes. It is nonlinear and the degrees of freedom are huge. So that's why biology is a lot more complicated than a physical system. Physicists don't understand the complexity when they come into this field, because this level of details are not normally taught in biology classes at the lower level. Okay, so when we have so one problem is that we don't have mathematical techniques to deal with very large number of nonlinear systems. And when that happens, what we have to resort to some techniques which is called machine learning. Machine learning can help because data is unreasonably effective. You can learn from the data. That is the point I'm trying to make here. If you look at a cancer, the normal cell will turn into cancer probably because of genetic variations like mutations, and there is also something called epigenetics, which I'm not going to give details here. Epigenetics are some marks on the DNA, meaning DNA doesn't change, some characteristics of the DNA changes, and that can also give you cancer. Or some expression variation, some protein overexpression. Even if there is no DNA mutations, the regulatory process can be dysregulated due to whatever reasons. But what happens, what now we have the ability to, is to measure these changes in tumor sample. So what can we do with these molecular profiles? So if you have molecular profiles from a whole lot of tumor samples, you can compare the tumors. If you have breast tumors from several individuals, you can get normal cells from matched normal breast tissues from individuals. You can compare and see what changes happen. And that can give you an idea about how to treat the patient better. Because, for example, there is a type of breast cancer called HER2 positive, meaning there is a particular protein which is overexpressed in that tumors, for example. And those patients used to perform very poorly in the olden days. But once you identify those proteins, there is a molecule to inhibit that protein, and which has given incredible success rate for people who have that particular kind of breast cancer. So another important thing is that not all patients will do very poorly. For example, there are prostate cancer patients. Some of them, even if you don't treat them, they have a very good prognosis. And treatments which we give now are reduce the quality of life because it's chemotherapy. But for a doctor, there is no way to identify who is going to do well and who is not going to do poorly. If there are biomarkers which can identify with very high sensitivity and specificity the kind of patients who need aggressive therapy, it can change, revolutionize the way we treat cancer patients. So that's one very important thing which we try to do. Develop biomarkers to identify these, to classify the patients into good and poor prognosis. And another thing which we have noticed many years, decades back, we knew that cancer patients their clinical outcome is very heterogeneous. But what I mean by that is that if you take a group of lung cancer patients, some of them do very poorly, meaning they will not survive more than 1 year. There is a subsection of people who will survive longer. And how do we identify this? In an unbiased manner. These are the kind of problems where machine learning can help us, and I will give you some examples of that. Let's skip this. So, like I said, when you have data from large number of cancer patients and normal individuals, you have two different ways to attack the problems. There are statisticians who will use statistical models, whereas computer scientists will try to look at machine learning algorithms. And these are all things which we do in a routine manner to understand the biology. And some of you may know, but I'm going to give a very cartoonish way of what's different between a traditional programming approach to a problem and machine learning. In a typical computational solution, you have you can program all the rules you have, if you know the rules. Then if you have input data, you can actually get the labels, or meaning decisions. And we have to encode all the rules into the program. The problem with very complex system is that you don't know the rules in advance. So for example, if you look at the transcriptomic profile, you can think of it as a vector of dimensions 26,000. There are approximately 26,000 genes in a human body. So if you have, say, 100 patients who did poorly and 100 patients who had good prognosis, if you want to derive rules, you don't know how to come up with those rules. And that is where machine learning, if you have known labels and input data, you can have a machine learning algorithm which will give you the output of the algorithm is the rules which you can apply to new data sets. Alright, so I will give you some success story in breast cancer. This was a classic paper published in 2000 in Nature, Molecular Properties of. This paper has revolutionized the way we treat breast cancer patients. This was done in Stanford University. They did gene expression profile of about 78 breast cancer patients. At the time, they didn't have the technology to measure the expression profile of all genes. They had expression levels of approximately 8,000 genes. And what they did is that they just clustered the samples. Hopefully, what clustering does is to kind of put expression profiles of samples that are similar next to each other. It's a very simple, I would even say a silly clustering algorithm. There are more sophisticated algorithms than hierarchical clustering. But what they found was remarkable. What they found that you can actually classify the sample breast cancer patients into 5 different types because they are homogeneous, and they found that this is what is called survival curve, the probability of survival. For example, the people in this blue graph, this group of patients, have much higher, like almost everyone, more than 50% of them survive more than 141 months. Whereas people in this group here has very poor prognosis, which provides the doctors with very different ideas about how to treat the patients. And they can also learn some biology. For example, those poor prognosis patients have this particular gene overexpressed. That was the example I was giving before. Which then, and like for example, if you take the percentage of survival, in this group, 84% survive, I believe it is 5 years. Whereas in this group, only 52% survive 5 years. But even they learn some biology. For example, this group has overexpression of these genes, so they design small molecules which will inhibit that gene and came up with what is called tailored therapy. Before this, almost all breast cancer patients were given same chemotherapy, but because we understood the biology better, you can give different. For example, the very poor prognosis people have a drug called Herceptin. And what happened is that after this kind of tailored therapy was introduced, the survival rate of breast cancer patients has improved by 91%. Most of breast cancer is not a very serious disease anymore. Because of that one, it has been reproduced by several other groups and modified for better. We have even better markers now to tailor the therapy. Right, now I'm going to give you present a problem which we are now working on. We have some solution which is not, I wouldn't say that we have solved it. So if any one of you want to work on something like this, so again, the problem is CUP. CUP stands for cancer of unknown primary. About 3 to 5% of the tumors, this is statistics I know from United States, about 3 to 5% of the patients, the doctors don't know where the primary tumor is. Meaning, the tumor is identified, for example, in lung. And the pathologist will look at it and say that this is tumor, but I think it is not from the lung, it is from somewhere else, it is metastasis. There are several problems with that. One, these patients cannot be treated. Right now, the treatment is tissue specific, meaning a lung cancer is treated very differently from a colon cancer. And CUP cancer, because you don't know the primary, you cannot give the best treatment, you will give you a conventional chemotherapy. Second problem is that they are much more prone to have depression or other, because they know that there is some other tumor somewhere, they don't know where it is. And why does that happen? Because cells migrate, and cancer cells by definition will acquire the ability to metastasize. So this I got from this website where they showed which is the most likely places for a typical cancer to metastasis. Okay, so this is what I was telling you, about 5% of the cancers are from unknown primary. And like I said, an additional problem is that a breast cancer can be classified into different subtypes and treated out differently. But if it is a CUP, if you detect the cancer in the lung, but didn't identify it as the breast cancer, the patient cannot avail that advantage. Consequently, the CUP patients have very poor survival. Median survival is 11 months, meaning 50% of the people will die before 11 months, no matter how you treat them. So, there is this project called Cancer Genome Atlas Project. This is funded by the National Cancer Institute. What they have done is, they have taken 500 tumors from 30 different tumor types and profiled it using the most expensive technology. And they have put that data on a website. Anybody can download it. So you can say, for example, a particular breast cancer patient, data can be a vector of 26,000 dimensions. About 10,000 samples have RNA measured using RNA sequencing technology. What that means is it's much more reliable than non-RNA sequencing technology. There are microarray based. So what we did was, okay, so we took that data set of 10,000, so think of it as a matrix. You have 10,000 samples and 26,000 genes. So you have a matrix of 10,000 by 26,000. You can't visualize something which has 26,000 dimensions. So there are some dimensionality reduction methods, meaning you can find linear combination of these gene expression patterns, and this is a three-dimensional representation of that big data set, and it is color-coded by different tumor types. And there is in my PC there was if you click on this portal, this is available, anybody can access this portal and play around with this. You can see that samples, profiles from similar tumor types will cluster next to each other, which gives us the idea that we should be able to derive a classifier to identify the tumor type. That is the fundamental observation. Another thing which we learned that within the TCGA dataset, they have also provided some normal tissue. What they do is when they do the biopsy of the patient, they will take some tissue next to the tumor sample. Please tell me when I have to stop. So, what we can see from here is that even the expression profile of the normal tissues are close to the tumor tissues. What that tells me is that you don't need to have a huge amount of shift in the transcriptional profile to make a tumor cell, a normal cell tumor. So, we thought of deriving a classification algorithm. We also have some normal tissue expression from another project from NIH again, GTEx. So, people from the machine learning field will know this. We developed a strategy called K-fold consolidation, in this case 10-fold consolidation. By that what I mean is that we divide the 10,000 samples into 10 different buckets. We'll put one bucket outside for testing, develop a model with the remaining, and apply that model on the left-out thing, and we will do that on a round-robin basis. In that process, what happens is that we can estimate the accuracy you would get for a new sample, because the test dataset is not seen by the model in the model development process. So, I'll skip. So we tried very different classification algorithms, and this is a bit slow, but you have to believe me, this data is available, in this bioarchive paper. It is not yet published in a peer-reviewed journal. We are trying to get this published, but long story short, we have very high accuracy in most of the tumor types. Meaning, if you give me a tumor expression profile, I should be able to tell you what is the primary type. With pretty reasonable accuracy. So, if you have a cancer of the non-primary, you should be able to tell you what is the primary type. The patient should be able to get better treatment than what is the primary. And Jackson Lab. So, I forgot to tell you, Jackson Lab is the place for mammalian genetics. What we use is mouse as a model. We have this program called patient-derived xenograph. What we can do is that we can take a human tumor and implant it on an immunocompromised mice. If you put a human tumor in a mouse, normal mouse, it will not grow because the immune system of the mouse will kill it because it's a completely foreign object. But we have engineered mouse to deplete it of its immune cells so you can grow the tumor in mouse. And that provides us several advantages. You can photocopy, it's like photocopying tumor. You can have hundreds of mouse with the same tumor. And then we can have different treatments to see which works for this particular tumor type. Which is not possible because you cannot have the same treatment on the same human patients. So we had expression profiles of different tumors from PAIN-3DX, patient-derived serum blast. And we used that dataset as validation set, and we were able to get, again, very high accuracy. Now, there are some problems. We submitted this paper to different journals, and one of the criticisms is that we have some mistakes. For example, stomach cancers are often misclassified as colon cancer, which is not a good thing because they are treated very differently. The problem is that they are very similar, they are very adjacent in the developmental stage. These cell types are next to each other. So that's the problem we have to solve. Additionally, to make something like this useful in the clinic, we need to reduce the number of features, because if we want to use RNA-seq for a cancer patient, it's a very expensive process. So we are trying to develop classifiers which use less number of. If you can reduce it to 800 genes, then it can be much cheaper, something like the order of 3,000 rupees, $50 or something like that. to do that. So that's what kind of things which we try to do in our group to give you a flavor of this. So what I want to tell you is that in biology we generate a lot of data. What I showed you here, these are all what we call bulk RNA, meaning we take the tissue and we have one expression profile. We know that it is not right because a tumor tissue consists of very different cell types. The epithelial cells which are actually becoming tumor, also the immune cells. We know that what the kind of cells surrounding the tumor tissue can determine the clinical outcome. So right now there are technologies to generate single cell RNA, meaning if you take a tissue, instead of 126,000 vector, you will get a matrix of 10,000 by 10,000. So it's a huge data set. How do we make sense of that kind of data sets? So again, machine learning, I believe, is the answer. There are many different kinds of machine learning techniques that are being used in this field. Due to the lack of time, I will not go into those kind of things. If you look at bioarchive, you can see research for machine learning in medicine. You can find enormous number of publications happening. The beauty is that there are a lot of data sets available in the public. The cancer genome atlas data is publicly available. Anyone can download it and organize it into a computable matrix format and work with that. You can, if you go to this paper, you should be able to find the sites where those data sets are available, accessible. I want to leave you with a note, which I have been thinking about a while, but we don't have access to. Imagine that we have data, longitudinal data from patients. For example, we know that there are a lot of diseases that comes. The technical term is comorbidity. By that what I mean is that if you have type 2 diabetes, you are much more likely to develop kidney problems or even Alzheimer's at a later stage. Those are things which doctors know. But we don't know other comorbidities. But imagine you have data sets where you have longitudinally tracked people based on what infections you have at a younger age, what kind of diseases you develop and believe me, there are a lot of mechanistic reasons why that should happen. There are some initiatives now to do something like that, which will again open up people like computer scientists or even any engineer to come into this field. Because you need to work with big data sets and compute with it. Statisticians are typically challenged when you have to deal with huge data sets. Engineers, on the other hand, are not that statistically sophisticated and put in models which are not appropriate, to be frank. So, this is an area which is very interdisciplinary, and unlike what was told here, like anyone can be. We want people from an engineering background to come into this field. The challenges are many, there are opportunities abundant, and I hope some of you will look for projects in this area or even do graduate level courses in this area. The CUP team, I just want to acknowledge the people who work with the cancer of unknown primarily. William Flynn is the main person who did a lot of computing because his data sets be processed in the cloud, and these are the people who are involved in that project. And I will stop here, and I hope I can answer. Take some questions if I may.